the device used to convert heat into water. The device used is heat engines. So heat engine is a device which converts heat into water. How it works, it receives heat from a source at high temperature and it converts heat into work by rejecting heat to a sink at lower temperature. The schematic arrangement is shown here. So there is a source. Source is the body of infinite heat capacity. If you draw heat from it, its temperature won't change. In the schematic, the temperature of the source is T1. And from the source, the heat engine, draws heat and rejects heat to sink. Sink is another body which can take up any amount of heat without the change in temperature. While taking and rejecting heat, this engine converts certain quantity of heat into work. In our example, or in general, let the engine takes heat Q1 from the source and rejects heat Q2 to the sink. So how much work can it deliver due to this heat addition rejection? So that is W net, which is equal to Q1 minus Q2. So out of Q1 quantity of heat supplied to the engine and the Q2 quantity of heat rejected by the engine, the difference in these two quantities is delivered as work by the engine. Practically, we can think of an engine like this. So there is a boiler. We can add heat inside the boiler to your working fluid. So working fluid here is steam. And for initially water is present inside the boiler. And adding heat, it is converted into steam. So the steam is at high pressure and temperature. It is sent to the turbine where it expands and rotates the turbine, producing energy, that is work. That steam is taken to a condenser where it rejects heat. And the steam is condensed to water. The water can be reused by pumping back into the boiler. So working fluid is a substance upon which we focus our attention. Therefore, we can say working fluid as a system. It takes heat at one location and rejects heat at another location. And at one location, it delivers work turbine, and at other location, it takes work pump. So it is a cyclic process. Water is converted into steam, produces work at the turbine, condensed back to water. Again, it is pumped into boiler for steam generation. So it is a cyclic process. And for first law of thermodynamics, we know sigma W equal to sigma Q. W is the work transfer, Q is the heat transfer, and W net is equal to Q net. What is this W net? W net is equal to W of T minus W of P. So W of T is the work delivered by the turbine. W of P is the work consumed by the pump. Therefore, it is negative. And Q net is equal to Q1 minus Q2. Q1 is the heat added to the system, that is a working fluid steam at the boiler, therefore it is positive. And Q2 is the heat rejected by the system, that is the working fluid steam at the condenser, therefore negative symbol. So having understood how heat is converted into work, our next aim is to focus on what is the efficiency of a heat engine. So the thermal efficiency of a heat engine is defined as net work output divided by the total heat input. Simply efficiency equal to output by input. Output here is the work delivered by the engine, maybe a turbine. The input for that we are adding heat. So the heat is added at the boiler. What is the quantity that is added? It is Q1. What is the work to produce? It is a net work. Net work is nothing but WT, that is a turbine work, minus pump work. This can be written as efficiency equal to Q1 minus Q2 divided by Q1. What is the W net? W net is the net work delivered by the engine. From first law, applied for a cycle, we know net work transfer is equal to net heat transfer. So what is the heat transfer? It is equal to Q1 minus Q2. Net work transfer, W net is equal to net heat transfer. Heat transfer is Q1 minus Q2. Therefore, instead of W net, we substitute Q1 minus Q2. This can be rewritten as 1 minus Q2 divided by Q1. This is the equation for calculating the efficiency of a heat engine. From the ongoing discussion, we are about to discuss or we are about to define second law of thermodynamics called Kelvin-Planck statement. What is Kelvin-Planck statement? It is impossible for a heat engine to produce net work in a cycle if it exchanges heat only with bodies at a single fixed temperature. What it implies is for an engine to operate, Q2 must be greater than 0. What is that Q2? Q2 is the heat rejection. Without heat rejection, a heat engine cannot work. So this is what Kelvin-Planck statement for second law of thermodynamics. This implies W net is never equal to Q1. And hence, efficiency of a heat engine cannot be 100%. A heat engine therefore has to waste some heat to produce work. Why we call it as a waste heat? Because the quantity of heat rejected by the engine Q2 cannot be recycled or it cannot be utilized again. Therefore, certain quantity of heat goes as a waste. Without wasting heat, we cannot produce work. This is what Kelvin-Planck statement. And hence, working fluid has to exchange heat with two reservoirs. Reservoir is a heat reservoirs. One reservoir is source, the other reservoir is sink. Our discussion leads to a definition called perpetual motion machine of kind 2. What is that? A heat engine in which Q2 equal to 0 and produces net work violates Kelvin-Planck statement. And that kind of machine is called perpetual motion machine of kind 2, PMM2 abbreviation. It is impossible because it violates second law of thermodynamics. Thank you.